All right, so moving on to switches. So switches are basically just make or break connections between conductors. They can be manual switches, like your light switches at home, where you physically toggle them on and off, or they can be things like electromechanical relays. Even semiconductors can behave as switches, as we'll see later. But for the ideal resistances, when we think of the resistance of a switch in a perfect world, when the switch is on, there would be 0 ohms resistance, perfectly short circuit, allows current to flow totally freely. And then in the off position, there would be infinite resistance, absolutely 0 current possibly flowing. So with a double throw switch that they show here in the circuit here, we can produce highs or lows at a particular output by just connecting the output to either, in this top example, the 5 volts directly, or, because this is 5 volts here, so we can connect it to 5 volts directly and get a 1 at the output, or we can flip the switch over to ground, which is always 0 volts, which would then produce a 0 at the output. So one type of switching device we can use is an electromechanical relay. This kind of device has physical contacts that physically make contact or disconnect. So there's physical metal contacts that are doing the switching, and this switching device uses specifically, it uses magnetic energy from a coil, and we energize that coil with some sort of external voltage to operate the switch and flip it on and off. You'll see these two terms often when talking about relays, about switches in general, but especially about relays. You'll see NC or NO to describe if it's normally closed or normally open. Normally closed meaning the default state, if you don't apply any external voltage, you just have the relay sitting there, no power applied to it at all, the default state is closed, the switch is closed. And then, of course, normally open, meaning no power applied at all, the default state is that it's an open circuit. The nice thing about electromechanical relays is that they provide good isolation because it's physically opening and closing a physical connection. So when you disconnect 2 wires from each other, there's pretty good isolation between the two. That you're not going to, you unplug something from the wall, you'd be pretty sure that there's not going to be any current flowing through that plug anymore, because you're physically pulling it apart. But it does require a triggering source, and that triggering source, when you apply power to the device, then it can produce an output on the 2 contacts. So the problem, though, is that relatively high current is required. Not ridiculously high currents, not on the order of amps, but, still compared to, especially like semiconductor devices, which we'll get into in a little bit, semiconductor devices can do things, can switch on and off with relatively little current, very little current. Relays, because you need enough energy to physically move metal arms or metal contacts. It does require more current, and it's also slow because, again, you're physically moving something. It's going to take something on the order of milliseconds to actually switch it, which sounds small, but when you compare it to things like transistors that work, on the order of micro or nanoseconds, it actually is pretty slow. But they are useful for high current applications, again, because of that isolation, the good isolation that they have, and because you can physically make the relay big enough to withstand high currents that would that might otherwise fry transistors. So here's a diagram showing how these relays actually work. So on the left here you have a normally closed relay. We'll start with this one. Right now it's in its default state. You can see the two contacts here are touching. The switch is closed. So now X1 is now connected or short-circuited to X2. If we apply power to these contacts here, we power up this coil and create a magnetic field that's going this way, it's pulling this way. There's going to be a magnetic attraction between the bottom, this X2 arm, and the coil, and it's going to pull the X2 arm down and disconnect these contacts. So by default, before we applied power, it was a normally closed relay, so these contacts were closed. We apply power, now we pull these contacts apart, and now it is an open circuit. And then the opposite for this normally open relay on the right, by default you can see that the contacts are open. So it's an open circuit between X1 and X2. If we apply power to C1 and C2, power up the coil, same kind of magnetic field that we'll see. But this time, because instead of X2 being the arm that sticks out over the coil, X1 is the arm that sticks out over the coil, so it's going to get pulled downward into X2, and the contacts will come together and close the circuit. So here, that's just those two diagrams again, but then this bottom picture here is showing actual relays in real life. They can be in little tiny dip packages like this, or they can be, particularly in higher current applications where you need the thicker wire and just the overall beefier components to support high currents. Some of the big boy relays are they look something like this. So here's an example that so there are two diagrams here. This left one is just showing the overall kind of like the system view of this is showing how the clock oscillator is connected to the relay R1. R1 in this on the right side diagram, it looks like a capacitor. They're actually they're trying to represent a relay. So this is actually a relay, not a cap. But also note that it's a normally open relay. And we have this clock oscillator connected to it that's generating this signal here that they show us this timing diagram for. And it's oscillating between 0 and 5 volts over and over again. It's a clock signal, so it's just constant oscillation. Now, they want us to draw a timing diagram for V out right here based on this clock signal. Now, because we know this is a normally open relay, the first state that the clock is in is 0 volts, meaning it's off. It's not activating the relay. So the relay is going to take on whatever default state it takes on, which this particular relay is normally open, so it'll be open. So at the very beginning, the switch is off. You can think of it like that. If we were to activate the relay, the switch would move in this direction, flip to the other terminal and turn on, but that's not the case yet. So currently, with the clock set to 0 volts, our relay is in the off position, or open. So what does that mean for V out? Well, if this is an open circuit, there's nowhere for current to go from this 5 volt source up here down to ground. There's nowhere for it to go, so there's no current flowing through this resistor. Now, I don't know how far you've gotten in other circuits classes, but there's a law called Ohm's law that relates voltage, current, and resistance like this. Voltage is equal to the current times the resistance. Voltage here is actually the voltage drop. When we use Ohm's law, we're talking about the drop in voltage across a resistor, meaning how much does the voltage change from here to here. before the resistor and after the resistor. So the voltage drop is going to be equal to the current times the resistance. Well, if it's an open circuit, like I said, there's zero current, so the voltage drop would be zero, meaning the voltage isn't going to change from 5 volts at the top to when it gets to V out. It's still going to be 5 volts. So at the beginning, while the clock signal is 0, we'll go ahead and draw our V out. I'll just abbreviate it VO. It's actually 5 volts. It's high. Or it's a 1. Now, when we flip the clock signal to a 1 and activate this relay, what's going to happen is the relay is going to switch closed. So now, if I can, yeah, there we go. Now this circuit is closed. It's basically a short circuit between V out and ground. If V out is shorted to ground, it's forced to be 0 volts. And then of course current, if this node is 0 volts, then of course there's a voltage drop across this resistor of 5 volts. So then you could use Ohm's law to figure out how much current based on the resistance would be flowing, but that's not what they're looking for here. We would actually be done here figuring out what V out is, because we know it's connected to ground, therefore it must be 0 volts. So VO drops down to 0 when clock goes to a 1. And because this is a periodic signal, we expect the same thing to happen over and over and over again, because this clock signal is just, it's periodic. So we would see the same behavior from V out in each of these other clock cycles. And if you notice, V out is really just following the opposite of the clock signal. So when the clock is low, V out is high. When the clock is high, V out is low. So we know that the rest of the signal would look something like this. So moving on to diodes as switches. So a diode is a semiconductor device, and they don't show it here, but I'll go ahead and draw it. The symbol for a diode is a little triangle with a flat thingy at the top of the tip of the triangle. So a diode, you can think of it as current flowing in one direction. It's allowed to flow in one direction only. And the condition in which it allows current to flow is this one here, when the anode is more positive than the cathode. So the two sides of a diode are the anode here and the cathode here. I remember it by thinking A comes before C, meaning A is on you think of it as the beginning end of the diode. Here's because the diode looks, this triangle looks like an arrow facing left to right. So if you imagine current flowing, it would flow through the anode first, then the cathode. So A comes before C. That's just how I remember it. But if the anode is more positive than the cathode, as in if the voltage on the anode is greater than the voltage on the cathode, current's going to flow from the anode to the cathode. It's going to conduct. That is called forward bias. The opposite condition, if A is less than or equal to, for current to flow, A has to be greater than C. The anode has to be a greater voltage than the cathode. If it's not, this is called reversed bias, and current's not going to flow. It's not going to flow the opposite direction. No, it's just straight up not going to flow at all. So it would function as an open circuit. And in that way, it functions kind of like a switch. So forward bias, current flows. Reverse bias, nope, not going to flow. So then they show a diode here in a circuit with just a light bulb, They have a 5-volt source here, and remember that with these symbols for the DC power sources, the side with the long line is the positive side, and the side with the short line is the negative side. So the long line here means that this is the 5-volt side, and the short line here indicates, we're going to assume it's a 0-volt voltage level, which means if we trace this all the way back through the light bulb is kind of just like a resistor, basically. So we're going to see 0 volts, or at least close to 0 volts. Even if there is a voltage drop across this light bulb, it's going to be, what we can say for sure is that this voltage is going to be less than 5 volts. So because we know that the anode here, which is 5 volts, is less than what the cathode is, we know that current's going to flow. There's going to be, so the anode is more positive than the cathode. This is forward biased, and we're going to see current flow, and that light bulb in turn light up. So then this right-hand side circuit, we've basically just flipped the battery around. So now 0 volts is on the anode. 0 volts is on the anode. 5 volts is now here on the other side. We know that whatever this voltage is here is definitely going to be greater than 0 volts. It's not going to be 0 volts. It's going to be greater than 0 volts. Therefore, this is reverse biased. It's not going to, current is not going to flow, and we will see the light bulb not light up. So this is just another way of visualizing it. A water system check valve where, you know, normally current flows through left to right. So the water, this big piece here is on the top is on a hinge, so it can swing back and forth. And when water normally flows through it, it pushes that hinged door open, pushes the door to the right, and the door swings open, allows water to flow through. But then if we were to try and reverse the water flow, if the water was going right to left, it would push up against this door and swing it back the other direction. But this piece, this bottom piece here, is just tall enough to snag the very bottom of this door and keep it from swinging any further. It's essentially going to close up this valve, and water would not be able to flow. So in this way, it's kind of like a diode in the sense that water can go this way, but it cannot go this way. So just another way to visualize it. So the thing about a diode, though, is that it's not a perfect short. As we said, with ideal switches, we would want the resistance to be 0 ohms, perfect short, no voltage drop whatsoever. Unfortunately, with a diode, there is a voltage drop, and it's about 0.7 volts, and it's pretty consistent. If you look at this graph, at the point where the forward voltage, and remember, this is the biased voltage, meaning the voltage across the diode, the anode voltage minus the cathode voltage. If the voltage, so once it hits 0.7 volts and activates, you can keep, increasing the current based on whatever other components you have in the circuit. You can increase this current and keep increasing and increasing and increasing with a relatively little change left to right, right? Up here, with this very high current up here is still, if you trace the line down, it's still around 0.7, but this voltage here doesn't change much the more you increase the current. So we can for the most part assume the voltage drop across the diode is going to be 0.7 volts. Now, this is just a visualization of that. See, in an ideal situation, in an ideal diode, it would function as basically just a short circuit. On the left here, this diode would short, and there'd be 5 volts on the anode, and because this is a perfect short, there'd be 5 volts at V out after the diode. But because of that 0.7 volt drop, you can actually imagine it as an ideal diode, perfect short. However, there's this 0.7 volt reversed voltage that's basically subtracting off 0.7 volts from your original source voltage, which in this case is 5. So 5 would drop down 0.7 volts as it crosses the diode, and therefore this V out node would be at 4.3 volts. So here are just 4 diagrams. They want us to determine whether they're forward or reverse biased. So we'll start with the upper left. Here we have 5 volts at the anode, right? Here is 0 volts on ground. There may be a little voltage drop here across this resistor, but we definitely know it's not going to be 5 volts. If this were if V1 were 5 volts, then, or no, sorry, it wouldn't be 5 volts. We know it's something less than 5. We know that now this is forward biased, and current will flow because the anode is greater than the cathode. Now, the second one in the upper right here, this one, here's 0 volts at ground. 5 volts is directly on the cathode this time. We know that V2 is something less than 5. It's coming from ground, so it's something less than 5. We know that this cathode is greater than the anode, so this is reversed bias, and it's not going to allow current flow. Then in the lower left, we've got 0 volts on the cathode. We've got something greater than 0 volts on the anode because of this 5 volt source here. So we know that the anode is greater than the cathode, so we can say that it's forward biased. And then the last one here, 0 volts forced on the anode. The cathode is something greater than 0 because of that 5 volt source over here. So we know that this is, so the cathode is, so the anode is less than the cathode. So we know this is reverse biased. So then moving on to transistors as switches. So one type of transistor is the bipolar junction transistor. It's also known as a BJT for short. It has 3 terminals, the base, emitter, and the collector. And the way it works is that an input signal at one terminal generates a short between the other 2. So just to skip over to the few slides from now, just to show you a diagram. There's our on that middle diagram here. This is showing the base, the collector, and the emitter. And how this works is, as they worded it, an input signal at one terminal generates a short or open between the other 2 terminals. What they mean by that is applying some voltages to the base here is going to generate current flow, or allow current flow, from the collector to the emitter. So the base is acting as the trigger that allows current to flow from collector to emitter, which is essentially making the collector-emitter relationship like a switch, with the emitter on one end and the collector on the other, and the base controlling the arm of the switch, whether it's flipped on or off. So that's the general idea. Now to go back to that other slide, there are 2 types of BJTs, NPN and PNP. Really, they refer to, let me go back to that diagram, that first diagram on the left. It's referring to basically the materials inside the transistor and how they're organized. There's 2 N materials and a P material sandwiched in between them. Technically, that's what NPN and PNP mean, but in this situation and for this chapter, we're really just focusing on how they function. NPNs and PNPs function differently, and we'll see what the differences are, but those are the two types. So first of all, NPN, the condition, like I said, there's a condition on the base terminal that creates a short between the collector and emitter terminals. That condition is that first point there, a positive base to emitter voltage. Meaning, if we just go to this next slide real quick, base to emitter, these two terminals, the relationship between them is you need a positive base to emitter voltage, meaning base has to be greater than emitter voltage. When that condition is true, it'll activate this transistor and allow current to flow. So when this happens, the transistor is said to be on. A negative voltage or zero voltage between the base and emitter opens up the transistor output. So if the emitter here is greater than or even just equal to the base, if the base is not greater than the emitter, then it's going to basically open up that switch between the collector and emitter and create an open circuit. And in that case, the transistor is said to be off. So here's just a representation of the diagrams for a BJT, and then this third picture is just real life transistors, real life BJTs. They have a dime for size to show you that they're relatively small. So in this example here, with this 2-volt supply on this resistor, and just as a note, you can expect the current draw in this direction to be relatively small. Small enough that you can consider the voltage drop to basically be zero. That there's so little current flowing through RB that the 2 volts at the 2-volt supply is also 2 volts at the base. So if our base is 2 volts and our emitter is connected to ground, which means it's forced to 0 volts, this is a situation where our base is greater than our emitter voltage. So this would activate the transistor and allow current to flow from collector to emitter, and that would mean the transistor's on. In that case, when current is flowing, think of it like a short circuit. This ground is now shorted to the Vout node, so Vout is of course 0 volts. Now if we take that 2-volt supply and we switch it over, we take it out and just connect ground directly to that base resistor, we now have 0 volts on this resistor, therefore 0 volts on the base. The emitter is also 0 volts. Because the base is not greater than the emitter, this is going to create basically an open circuit. Now, if this is an open circuit, as before, there will be 0 current going through this resistor because it has nowhere to go, and therefore there will be a 0 voltage drop. This 5 volts will not drop at all as it goes through, or not that it's going through the resistor because there's no current, but moving past the resistor, this 5 volts will remain the same. Therefore, Vout is going to be 5 volts. So then just to cover PNP transistors real quick, it's kind of the opposite. We want a negative base to emitter voltage to short the transistor output, to turn the transistor on. And we want a positive voltage or 0 volts base to emitter to open it or turn the transistor off. So in our other examples, if I go back to this slide, if this were a PNP transistor, we would want the condition to switch the transistor on and short the collector and emitter would be that we actually want the base to be less than, not 0, the base to be less than the emitter. if the base is greater than or equal to the emitter, no current is going to flow. So it's basically just the opposite of an NPN transistor. All right, so for this example, they want us to sketch a waveform at Vout in this circuit, given the input signal clock, CP. And the clock is off at first, and then it switches on, off, and so on. So this is pretty much identical to this left-hand situation on this slide, except instead of this 2-volt supply, we have this clock signal that's going to vary between 0 volts and something greater than 0. Well, 5 volts. They show 5 volts here, but honestly, it could be anything greater than 0 because, well, you'll see why. So we have this setup where we have a resistor, and again, remember that very low current going through this resistor into the base of the transistor, so we can basically assume that the clock pulse shows up at the base as well. So in this configuration, the emitter is equal to 0 volts, right? All the time, because it's connected to ground. So now it's just a matter of what is the clock doing? If the clock is 0, this will be an open circuit. And the clock is 0 at first, at the very beginning here. It is 0 volts. So in that case, this transistor is off. It's an open circuit. Meaning, again, no current can flow through this resistor. Therefore, the voltage here, 5 volts, is going to be seen also on the other end of the resistor. So Vout would be 5 volts. So I'll draw Vout above the clock signal, but Vout will be high at first. Then the clock signal flips on, so now what happens? CP is now greater than 0, which means our base is now greater than our emitter. So it's going to flip this on, this transistor on, and short circuit it. Now, the collector is shorted to the emitter. The collector is connected to Vout. The collector voltage is Vout. Well, if the collector is shorted to the emitter and the emitter is on ground, that's going to force Vout to 0 volts as well. So now Vout is going to go low. And since the clock is just repeating itself, we would see the same thing happen. Now, so we're still seeing that the same response. So we can basically, and you'll notice that Vout is basically just the opposite of the clock signal. So we just draw the opposite. When clock is off, VO is on, and the other way around. So here are just a few discussion points. The 3 pins of a transistor that we talked about, of a BJT at least, the base, the collector, and the emitter. And remember that the base is functioning as the control. It determines whether the switch is on or off, but the switching actually happens between the collector and the emitter. When the transistor is on, the collector is shorted to the emitter. When it is off, it's an open circuit between the two. And then as far as NPN versus PNP, NPN, you turn a transistor on by having the base greater than the emitter voltage. PNP is just the opposite. You turn on the transistor by making the base less than the emitter. And actually, in both cases, both transistor types, if the base is equal to the emitter, it's going to be off. It has to be either greater than the base has to be either greater than the emitter in an NPN or less than the emitter in a PNP for the transistor to turn on. So now, just getting to what exactly TTL is. I think I mentioned it a few times already. Basically, it just stands for transistor to transistor logic. It's a way of using transistors to create logic, what we call logic gates, where you have an input, and on this example, this is an inverter circuit that they're showing here. But what we mean by logic gate is that we have one input. That input has stuff, it activates these transistors in a certain way that it's almost like, if you imagine V in goes into some black box. We have no idea what's, well, we have an idea of what's inside it. It's this, but just imagine that you have just a closed box that we don't know what's inside it. We just see V in go into it, and out pops V out. And this is a logic gate. So the circuits inside do something to V in, respond to V in a certain way, and produce a specific output depending on the purpose of the gate or how it's supposed to function. The inverter only has one input. There are other logic gates that we'll get to that have two inputs, so V1 we can say, and then V2, or often they'll be labeled with letters like A and B, and they produce an output. The combination of these two, and depending on what the values are that are input, the output gets set to something. So it's almost like this box is performing some sort of operation on the inputs and generating a specific output based on the inputs. And I think you saw that in the first multi-sim lab with the AND gate. The combination of inputs generated different results depending on which inputs were on, which ones were off. But basically, so this example they have is an inverter. You have an input voltage. It makes the circuit react. The way the circuit is designed, it's going to react in such a way that it's just going to produce the opposite voltage level of what was input. So if the input was 0 volts, it's going to output 5 volts. Or if the input was 5 volts, it's going to output 0 volts, just the opposite, or the inverse. And that's why it's an inverter, or called an inverter. So that's the first logic gate that we're going to talk about, of the several that we'll go over in the course of this class. But so the actual chip that we can use, there's a model called the 7404. It's a hex inverter, meaning 6 different inverters on the chip. And the pinouts are shown there, and the internal workings of it are shown there. That's the symbol for an inverter, a triangle with a little bubble on the tip of it. And that means take whatever goes into the input, invert it, and that's the output. There are 14 pins, 7 on a side. We need 2 pins. We need an input and an output for each one of these, and there are 6 of these logic gates. So we need 12 pins for the inputs and outputs of the gates themselves, and then the other 2 pins are for VCC and ground, because if you notice in that previous diagram, we do need some sort of power source, VCC, and typically you're going to, well, pretty much always match VCC to whatever your logic level is. So if you're saying that 5 volts represents a 1, you want this to be at least 5 volts, or you want it to be 5 volts. So it needs VCC and a ground, a reference voltage of 0, and those are very important. If you don't connect VCC or ground, either one of them, the chip's not going to work, or it might work, but you'll see some really funky voltages on the inputs and outputs. And this is this package where there's, one side of the chip has a bunch of pins, and then the other side of the other side of the chip has a bunch of pins. It's called a dual inline package because there are 2 lines or 2 rows of pins, and they're in line with each other, as in, they're parallel to each other. So on an actual chip, one thing that's that's common between all of these different logic chips, you'll notice this notch up here. That tells you what you can think of as the top of the chip, meaning it tells you where pin 1 is. Pin 1 is always going to be, if you think of this notch as the top, pin 1 is always the upper left. So that's how this chip is oriented here. If we could see the notch on this chip, it would be up here. So putting the notch at the top, we know that the upper left pin is always 1, and we go down the row of pins and then across, and continue the numbering scheme going up the second row of pins. And that's shown here. Pin 1 going through pin 7, and then pin 8's across from pin 7, and then pin 8, 9, 10, 11, 12, 13, 14 would go all the way up that chip on the other side. So there's this other kind of where we had TTL technology. This is a CMOS technology. It uses a different kind of transistor to accomplish the same thing. It's still, this chip is a CMOS inverter chip. It still inverts properly. It's just that the inner workings of it use CMOS transistors. MOSFET transistors. This alternative type of semiconductor being used, as opposed to TTL, the CMOS technology has relatively lower power consumption. It's useful in battery-powered devices so that you don't drain the battery too much. It is slower switching than TTL, and it is sensitive to electrostatic discharge, but those are the trade-offs. And by the way, just FYI, when you see NC on these pins here, 13 and 16, that just means no connect. They're not connected to anything, as you can see here. Totally empty. So then there's this term called SMD, and it refers to surface-mounted devices. While we saw here, these are our DIP packages. These pins are meant to go into through-hole, what they call through-hole circuit boards that have holes in them. Those pins go through the holes and get soldered on the other end of the board, on the other side of the board. SMD is surface mount, where, see if they have any. Yeah, so they do have pictures of that, and I'll show that in a second. But so surface mount devices are exactly what they sound like. They're mounted on the surface of boards, and this helps reduce the size and weight and the cost of manufacturing circuit boards. SMDs are mounted and soldered directly to a metal footprint on the surface of the circuit board, and they do require some special desoldering tools and techniques as opposed to through-hole chips, but this also allows chip densities to be increased, because instead of taking up two sides of a board because you're putting a pin through the board and soldering it, the device sits on one side of the board, the solder is on the other side, and you're taking up two sides. With SMD, now you can fit devices on just one side of the board, save some space, and therefore increase chip densities. And also SMD can handle higher frequencies. So here are just a few different types of SMDs and their footprints. You can see on the left so here's a small outline SMD chip, and you can see these little metal pads that they don't show the circuit board, but the circuit board's like here. There are these little metal pads that make contact with the pins, the little legs of this chip, and the legs get soldered to these metal pads. Second, here we have the PLCC, plastic leaded chip carrier. It's got these little kind of like wrap-around legs that extend a little bit underneath the chip too. You can kind of see there. We place these on similar metal pads, and then we solder those little legs to those metal pads. And these contacts go all the way around the chip, as you can see. It's on all four sides. And then finally we have a ball grid array, or BGA, another very common, especially with very high pin count chips, microprocessors that require a lot of pins. often use ball grid arrays because, you know, you can pack, here they show 4, 5, 6, 7, 8 by, I'm assuming 8, yeah, 8 by 8, so that's 64 pins that they can fit in this one area. So there are little, you don't see it in the picture here, but there are little balls, kind of like semispheres, little domes of contacts underneath this chip in a grid pattern, and those balls come in contact with the metal pads on the circuit board and are soldered to those metal contacts. And here's the lower left picture is just showing a dime to show you the size, the small size of these chips, and then the lower right is just the chips actually soldered to a circuit board. So surface mount devices, we talked about those three: small outline, PLCC, BGAs. The small outlines, they're dual inline packages. They have that gull-wing kind of pin, like little legs. It's typically for lower complexity logic stuff. PLCCs have leads on all four sides. They have that little J bend configuration. The bottom of the J is what makes contact with the metal pads on the circuit board. This is for more complex logic. Then the BGAs finally have the highest pin counts, higher than the other two, and connections for that are made through little round solder tabs on the bottom, and they're arranged in that grid format. And often these are used for micro controllers, microprocessors, because of just the density of pins. You know, things that require a lot of different pins, like CPUs and stuff like that, tend to use BGAs or some sort of grid array to save space with all those pins that they have. So to summarize the whole chapter, the digital level for a 1 is commonly represented by 5 volts in digital systems. In TTL logic, especially, we use 5 volts. Or I shouldn't say TTL logic, because it's transistor to transistor logic. So it'd be like saying ATM machine. But anyway, we use 5 volts in TTL and 0 volts for a 0. And that's just one common voltage. There are different systems that use different logics. Different microcontrollers might use different logic levels, but that's what you should look for, is keywords like logic level, or when they say something volt logic, like 3.3 volt logic means that it runs on 3.3 volts. But for the most part in this class, we'll be using 5 volts as our standard. We can use an oscilloscope to observe rapidly changing waveforms like clock signals or other digital signals, and we'll be using it a lot. And we'll be using them to observe, or we can use these oscilloscopes to observe these signals in a voltage versus time format, so that we can see over time how the signals are changing. The frequency of a clock waveform is equal to the reciprocal of the waveform speed, so that's that period versus frequency we talked about. We talked about serial and parallel formats for the transmission of binary data, serial being a single conductor and parallel being several conductors. Parallel having its advantages of being very fast, but its disadvantages of being prohibitively expensive, especially with when you scale things up into larger scales. Serial becomes a little bit slower, but it is much more practical. We talked about electromechanical relays, how they can be used to basically switch circuits on and off by creating shorts and opens. Electromechanical relays do require higher current values to drive it, because you're physically moving. You need energy to create a magnetic field strong enough to physically move metal conductors together and apart. But but it's not very fast either. Typically, you'll see relays more for higher current applications. Diodes can be used in digital circuitry when you need current to flow in only one direction, but not the other. Then we use transistors to act as switches by activating or deactivating them by applying the appropriate voltages. In the case of the BJT, it was applying a voltage to the base terminal, and depending on the relationship between the base and the emitter, if the base is greater, or in PNP transistors, if it's less than the emitter voltage, then you can switch the transistor on and off and create that short versus open kind of switching behavior. We touched on TTL a little bit. CMOS integrated circuits. They're two systems that do the same thing. They just use different transistor technologies inside, but they behave the same way. They create the same logic. A TTL inverter is the same as a CMOS inverter. It's just that there's trade-offs between each of the systems. These two systems are by far the most popular ICs used in digital circuitry. And then we touched on SMD, what SMD is, surface mount devices, and how they are, especially now, are very, very popular. They are preferred over the through-hole style dip ICs because of their smaller size, reduced manufacturing costs. You can cram more chips onto a circuit board, so the advantages of SMD and why we use them so much now over the through-hole style. But that concludes Chapter 2.